Am I audible?
Yes, sir.
So the last part of this course, that is vector space matrix, we shall discuss today. And I think the screen is visible. Or not?
Yes, sir, visual.
So what is a real vector space? You know, R represents the set of real numbers, and your R has the usual properties, you know. So a real vector space V is a set whose elements are called vectors and on which two operations are defined. One is addition of vector and second is multiplication of vector by real numbers. So V is a real vector space where the elements are vectors only. There shall be no scalars. So we denote elements of vector space by bold face symbols like or a symbol with the arrow sign, arrow mark uh, above the symbol like U vector, V vector, W vector as shown in the screen. Are you getting it?
Yes, sir.
Yes, sir.
So in addition of two vectors, that is the element of a vector space, is shown by your A having positive sign or plus sign, multiplication of a vector, multiplication by a real number V vector with a vector is written as A bold V, V in bold. So we use parentheses to separate quantities whenever needed. And elements of vector space must satisfy the condition of closure, which requires that addition by two elements U vector and V vector in capital V of a real vector space will result in an element that belongs to V. So if your U vector belongs to V and V vector belongs to V, then U plus V vector is also belongs to V, that is real vector space. If an element U of a vector space V is multiplied by a scalar A, then the resulting element AU also belongs to V. So if your U vector belongs to V and A is a scalar, then AU belongs to V. The operations of vector addition and scalar multiplication must satisfy 8 conditions. First is commutative, second associative, third zero vector, fourth your every vector V there exists a unique vector minus V, that is additive inverse, then distributive property, then distributive property with respect to addition of real numbers. Okay. Then successive multiplication by real numbers, then multiplication by real numbers 0, 1 and minus 1. And all are shown in the screen. You can go through it and if you have any doubt, please ask.
No, sir. No doubt.
So next is your a vector space is a set whose elements satisfy the 10 property set out of the equation I have explained you now. The elements of a vector space could be directed line segments, that is vectors, in the same sense that you know from your earlier courses, and functions, matrices and polynomials, etc. There are some worked out examples, you can go through it. Then a linear independence. Two non-zero vectors U and V are called dependent on each other if one of them can be obtained by multiplying the other by a real number. So a U vector is equal to a V vector or V vector is equal to 1 by a U vector. Otherwise, they are called linearly independent. The most important concept of linear independence can be generalized to any finite number of vectors. But first, a definition, let V1 vector, V2 vector, so on and so forth, VR vector be R non-zero vectors. A linear combination of these vectors is a vector of the type W vector is equal to A1 V1 vector plus A2 V2 vector plus so on so forth AR VR vector. Where A1, A2, so on so forth AR are real numbers. These numbers are called coefficients. So this set of vectors V1 vector, V2 vector, so on so forth VR vector is called linearly independent if none of the vectors can be written as a linear combination of others. Okay, so you can prove that your W vector is equal to A1 V1 plus A2 V2 plus so on so forth AR VR equated to 0 vector, and your W vector is equal to A1 V1 vector plus A2 V2 vector plus so on so forth is equal to 0, implies that all these coefficients are 0, that is A1 is equal to A2 is equal to AR is equal to 0. So the proof is shown in the screen. You can go through it. If you have any doubt, you can ask, and there is an example. So that the vectors U vector is equal to in matrix 1 0 1 and V vector is 1 1 1 matrix in Cartesian space are linearly independent. So what you have to do? First you have to find out A U vector plus B V vector. Then you can see that this is 0 or null vector. So this is true only if A is equal to 0 and B is equal to 0. So your U and V vector are linearly independent as per the theorem. Then linear subspace. A subset V, V1, which is a subset of V, is called a subspace of V. If V1 is a subset of V, which is a real vector space, so it is a subspace of that V. If all vectors in it satisfy the condition of a vector space. In particular, the 0 vector or null vector of V must be in V1, and given a finite numbers V1, V2, so on so forth, the VR vector of linearly independent vectors in a vector space V, we can denote by L the set of all possible linear combinations, that is A1 V1 plus A2 V2 plus so on so forth AR VR of these vectors by arbitrary real numbers A1, A2, so on so forth AR. Then the set W is a subspace of V called a linear span of your V1, V2, so on so forth VR. And if a vector space has only one vector, that has to be the 0 vector, because every vector space must have a 0 vector. So the set 0 vector is by itself a vector space called a trivial vector space. And a vector space V with more than one element will actually have at least one non-zero element. Okay, in a finite dimension space, no matter how we choose the basis, the number of basis vector will always be same. And integer n is called the dimension of vector space V, which is in the subscript. And we say that the vector space is finite dimensional. And in the process does not stop to keep finding new linearly independent vectors indefinitely, then we say that the vector space is infinite dimensional. So we can have our 2-dimensional, 3-dimensional, and higher dimensional space. Then we can change bases. Let V be a vector space of dimension n, and let E vector I to the power n I is equal to 1 be a basis in V. We write a vector V belongs to capital V as a linear combination of the basis vectors, as V vector is equal to summation I is equal to 1 to n x superscript I E subscript I vector. And this x superscript I, where I is equal to 1 to n, are called components of vector V with respect to the basis E. So the components of vector depends on the basis chosen. Then we can change the basis as shown in the screen. Then change in component with basis change. When the basis changes by a matrix T, then the components of the same vector change by the inverse transpose of the matrix as shown in the screen. Okay. Then direct sum of vector spaces. So let U1 is a subset of V and U2 is a subset of V with the two subspaces of V, such that apart from the 0 vector, which must belong to every subspace, there is no other vector common between U1 and U2. And every vector small b belongs to V can be uniquely written as the sum of two vectors u1 and u2 belongs to u1 and u2 respectively. So your V vector is equal to u1 vector plus u2 vector, where u1 belongs to capital U1 and u2 vector belongs to capital U2. So in such a case, we say that the space V is the direct sum of the subspaces U1 and U2, and we can write V is equal to your direct sum of U1 and U2. Then your linear operators. Linear operators are mapping between vector spaces, and if V and W be two finite dimensional real vector spaces of dimensions n and m respectively, then you can have a mapping, and the subspace K in course of discussion is called the kernel of the linear mapping T, and if the kernel has only the single vector, null vector or zero vector, then the linear mapping is 1 to 1. Similarly, you can have your product of operators as shown in the screen, then inner product and metric. A real vector space is defined by the operations of sum of its vector elements and multiplication by the vectors by of its vector by real numbers. An inner product or metric is an additional structure on the vector space, and the generalization of dot product to arbitrary vector space is called an inner product. Okay, the inner product of any two vectors V and W in a real vector space V is a real number denoted by U comma W, and the function which defines the inner product should have the following three properties. First is it is linear in the second argument, and second is it is symmetric, and third is it is non-degenerate. And what is represented by these things are shown in the screen. And a positive definite inner product is an inner product which moreover has the property that for every non-zero vector it is strictly positive as shown in the screen. Then orthonormal vectors. Given an inner product, we can define the notion of orthogonality. Two vectors V and U in V are called orthogonal if their inner product is 0 as shown in the screen. For any vector V, the number V comma V is its norm square. When the inner product is positive defined, as in Euclidean space, the positive number root over of V comma V is its norm or length. Okay, and a vector with 0 norm squared, that is a vector which is orthogonal to itself, is called a null vector. And a vector with norm squared equal to 1 or minus 1 is called normalized. So orthogonal vectors with norm squared equal to 1 or minus 1 are called orthonormal vectors. Okay, then your orthonormal bases. Am I audible?
Yes, sir.
So if EI vector where I is equal to 1 to n be a basis in real n dimensional vector space V, the components of the inner product or metric in this basis are Gij is equal to EI and EI comma EJ, and the symmetry matrix contains all the information about the inner product. Okay, and the non-degeneracy of the inner product means that G is equal to determinant of Gij, which is not equal to 0. And the matrix of the metric tensor components in any basis is non-singular. So this is such a basis is called an orthonormal basis, where in spite of existence of 0 norm vector in the space, we can always choose the basis as shown in the screen. Squared vector minus the number of negative norm squared vector is an orthonormal basis and is called signature of the metric and denoted by sig V. And there do exist bases which contains non-zero null vectors as basis vectors, but these bases are not orthonormal. And the zero vector always has a 0 norm, and in Minkowski space of special relativity, there are non-zero vectors that are called light-like vectors, and a light-like vector V has your V comma V is equal to 0. Because the metric of special relativity is not positive definite. Then you can have construction of orthonormal basis. This construction is called gram schemed process. Then singular, then a complex vector spaces or Hilbert space, and your signature of the metric, Hermitian inner product, Pythagoras theorem and Bessel's inequality, and your squares and triangle inequality. Then your orthonormal basis. So, an set in a Hilbert space H is called complete if it is not a proper subset of another set, and a complete set is called orthonormal basis. Then your terminal questions and some worked out problems, we can go through it. Then your matrices, and in matrix you have your linear equations and matrix, then your definition of matrix, which you know, then various types of matrix, then the transpose of a matrix and symmetric matrix, then complex conjugate and Hermitian adjoint, then inverse, orthogonal and unitary matrix, then functions of matrix, then matrix algebra, which you know, then there are some basic operations, partitioning of matrix, then your permutation and combination, and definition of determinant and its properties, and your proof of the Laplace expansion, inverse of a matrix, linear operators and matrix, and the last part is your eigenvalue equation and solution of x is equal to 0, then your eigenvector and eigenvalue, then inner product of orthonormal basis, then real orthogonal and real symmetric matrices, then your Hermitian and unitary matrix, and some worked out problems and SAQs. I think the screen is visible.
Yes, sir.
So you know these preliminary things. What is the definition of matrix? A matrix may be defined as a square or rectangular array of numbers or functions that obey certain laws. And these are shown in the screen. Then you also know the operations of matrix, equality of two matrix, addition, and the properties. That is, addition matrix is commutative, so on and so forth. Then scalar multiplication of matrix, matrix addition is associative, the identity matrix for addition is 0. Then your multiplication of matrix is possible. Then you know all these things, isn't it?
Yes, sir.
Then linear transformation, do you know it?
No, sir.
Okay. So consider a set of equations where capital X is equal to ax plus by and capital Y is equal to cx plus dy, where a, b, c, d are constants. Then you can express it in a matrix form as shown in the screen. Xy is equal to a b, c, d matrix multiplied by xy matrix. Or you can write R is equal to mr, where am is equal to your a, b, c, d A, B, C, D, and R is equal to X, Y, and R is equal to X, comma, Y. So, for every point X, comma, Y, this equation gives us a point capital X, comma, capital Y. If we think of each point of the X, comma, Y plane being moved to some other point, with some points like the origin not being moved, we can call this process a mapping or transformation of the plane into itself. All the information about this transformation is contained in the matrix capital M. We can say that this matrix is an operator which maps the plane into itself. So any matrix can be thought of as an operator on conformable column matrices small r. Since M R1 plus R2 is equal to M R1, capital M R1 plus capital M R2, and your M under M mu r is equal to K M R, the matrix M is a linear operator. So these things can be explained in a graphical form. So you can see figure 1.1 and figure 1.2. Your small r and capital R, then your in figure 2 there is a rotation of axis. And this is linear transformation, which I have also already expressed to you in group theory, your active transformation and passive transformation. Then there are some special matrices. So there are several special matrices which are related to a given matrix capital A, and we outline these in table as shown in the screen. Name of the matrix, notation of it, how to get it from A. First one is transpose of A, or A transpose R. This can be written as A superscript T, or A bar, or A dash, or A small superscript small t. How can you get it? By interchanging rows and columns. Do you know all these things? Transpose, complex conjugate, transpose conjugate, Hermitian conjugate, Hermitian adjoint, and inverse. I think you know all these things, or am I wrong?
Sir, can you explain please Hermitian
So
conjugate?
look Hermitian. You have to take the complex conjugate of each element and then transpose it, and it is written as A dagger. Okay. First you have
Yes, sir.
A. So how to get your transpose conjugate of Hermitian? So you have to first take the complex conjugate of each element in the matrix, then you have to transpose it. Okay.
Sir, can you please
Similarly,
give an example?
हाँ एग्जाम्पल देंगे आगे है एग्जाम्पल. Then inverse
Okay.
of A. Inverse of A is derived by the formula 1 by determinant of A multiplied by C to the power T, and it is written as A inverse. Then there are real matrix, symmetric matrix, then your orthogonal matrix, Q symmetric or anti-symmetric matrix, then pure imaginary matrix like Hermitian, which is A is equal to A dagger, then anti-Hermitian A is equal to minus A dagger, then unitary A inverse is equal to A dagger, then normal, that is A dagger is equal to A dagger A. Then your orthogonal matrix. So let us have a Hermitian first, which you are asking, then we shall go to these things, because this will be better for you. Let us see this. 1, 3, 3, 2, 4, 1, 3, 8, 4. So its complex conjugate of each number is real because there is no imaginary part. Then transpose it. So it is the Hermitian conjugate. Are you getting it? If you have an imaginary number, let us have an example. So here A is equal to 0 minus I 0. So the complex conjugate will be 0 I minus I 0. Then its transpose will give you transpose of 0 I minus I 0 will give you Hermitian conjugate. Are you getting it?
Okay, okay.
Is the screen visible?
Yes, sir.
Then your orthogonal matrix. A matrix A is orthogonal if its transpose is equal to its inverse. Okay? Unitary matrix. A matrix A is labeled unitary if A dagger is equal to A inverse. Then Hermitian matrix. The matrix A is labeled Hermitian or self adjoint if A is equal to A dagger. If A is equal to A dagger, then you can say that the matrix is Hermitian. If A is equal to minus A dagger, then matrix is not Hermitian. Let us have an example. A is equal to 0 minus I 0. So your A star is equal to 0 I minus I 0, which I was telling you. Then the complex, then its transpose will be 0 minus I 0. So you see that A is equal to its transpose. Okay, this is equal to this. So A dagger is equal to A, hence it is Hermitian.
Yes.
If A and B are two non-commutating Hermitian matrices, that is AB minus BA is equal to IC, then you can prove that C is a Hermitian. So your A dagger is equal to A, B dagger is equal to B, C is equal to minus I, AB minus BA. So your C dagger can be written as I, AB minus BA dagger is equal to I, AB dagger minus BA dagger. So your I, B dagger, A dagger minus A dagger, B dagger is equal to I, BA minus AB is equal to minus I, AB minus BA, and your A dagger is equal to C, hence it is a Hermitian matrix. Then solution of system of linear equations by matrix method. Okay? So these are long question type things. You have a problem and you have to solve it by knowing the technique. Matrix method are useful in solving system of linear equations. Let us have a system of linear equations a11 x1 a12 x2 plus so on so forth a1n xn is equal to b1. Similarly, a21 x1 a22 x2 plus so on so forth a2n xn is equal to b2. Okay, as shown in equation 1.23. So there are n inhomogeneous equation in the n unknowns. So we can write the equation in matrix form as a11, a12, so on so forth, a1n, a21, a22, so on so forth, a2n multiplied by x1, x2, so on so forth, xn matrix is equal to b1, b2, so on so forth, bn matrix. So the system of linear equations can be expressed in the matrix form as I am showing in the screen. So you can also write it as Ax is equal to B, where A is equal to the first matrix as shown in the screen, A11, A12, so on so forth, A1n, A21, A22, so on so forth, A2n, so on so forth, AN1, AN2, so on so forth, ANN. And your X is equal to X1, X2, so on so forth, Xn matrix, and your B is equal to B1, B2, so on so forth, Bn matrix. So the n cross n matrix A is called the coefficient matrix of the system. So X is a n cross 1 column matrix or column vector. So B is a n cross 1 column matrix or column vector. So you can assume that the coefficient matrix A and the matrix B are all known. So there are different solutions depending on the rank of the matrix A. So you can consider three different cases where B is not equal to 0, A is not equal to 0. Then your B is equal to 0, modulus of A is not equal to 0. Then B is equal to 0, modulus of A is equal to 0. So the matrix A, the first case, the matrix A is a non-singular one. So A inverse exists. So you can multiply this by A inverse, and your A inverse AX is equal to A inverse B, because your AX is equal to B and your AX is equal to A inverse B. So A inverse is equal to adjoint of A divided by determinant of A, and your X is equal to adjoint of A by determinant of A whole multiplied by B. So by Cramer's rule, you can have your Xi is equal to 1 by determinant of A, and you can multiply this with B1 A1i plus B2 A2i plus so on and so forth B and ANI, where I is equal to 1 to so on and so forth N. Similarly, if your B is equal to 0 and determinant of A is not equal to 0, then your AX is equal to 0 and your X1 is equal to X2 is equal to X3 is equal to Xn is equal to 0. And the unique solution is called the trivial solution. Similarly, if your B is equal to 0 and the determinant of A is equal to 0, your matrix A is singular. So the system has a large number of non-zero and non-trivial solutions. Let us have an example. So suppose there are three equations, x1 plus 2x2 plus 3x3 is equal to 8. The second equation is 2x1 plus 3x2 minus 4x3 is equal to 5. The third equation is 3x1 minus x2 plus 2x3 is equal to 10. Am I audible?
Yes, sir.
So you have to find out x1, x2 and x3. So what you will do? The steps as I have explained you earlier, you have to first write this in a matrix form. So in a matrix form, you can write it by taking the coefficients of x1, x2 and x3 in a matrix. So it will become 1, 2, 3, 2, 3 minus 4, 3 minus 1, 2, and will be multiplied by x1, x2, x3, and your b1, b2, b3 is 8, 5 and 10 in a matrix form. So it is in AX plus B format. So your AX and B are as I told you now. So your determinant of A is equal to 63 and it is non-zero. And your A inverse will exist. So you can have the formula format I have told you to solve it. So AX will be A inverse B. So that is adjoint of A B by A determinant of A. So by Cramer's rule, you have Xi is equal to 1 by determinant of A, then multiply it by B1 A1i plus B2 A2i plus B3 A3i. So you know your A11 is equal to 1 and your A21 is equal to your minus 7 and your A31 is equal to minus 17 and your A13 is equal to minus 11, A23 is equal to 7, A33 is equal to minus 1, so on and so forth. So you can write your x1 as 1 by minus 1 by 63, 16 minus 35 minus 170 is equal to 3. Similarly, your x2 will be minus 1 by 63, or 63 is its determinant, minus 128 minus 35 plus 100 is equal to 1. Okay, are you getting it how I am doing this? Or you are in doubt?
No, sir, no doubt.
Okay. So you know all these things. So your x1, x2 and x3 can be evaluated by this method and using the formula. Okay.
Yes, sir.
Okay. Then rank of a matrix. Rank of a matrix is the largest of the orders of all non-zero minors of that matrix. And it is denoted by R, where A is the matrix A. Suppose A is an n cross M matrix. So the rank of the matrix is R if there exists at least one non-zero minor of A of order n and every minor of A of higher order R plus 1, R plus 2, so on and so forth, 0. In other words, the rank of matrix A is the maximum number of linearly independent row vectors of A, and it is denoted by rank A. So let us have an example. Suppose there is a matrix A as shown in the screen, and it is 3, 0, 2, 2, minus 6, 42, 24, 54, 21, minus 21, 0, and minus 15. And you have your A is equal to this, then you can have convert it into a form where you have only maximum number of zero terms in the matrix, and here you can see there are two rows where non-zero terms are there, and hence the rank is 2. Then theorem 1, row equivalent matrices have the theorem 2, p vectors with n components each are linearly independent if the matrix with these vectors as row vectors has rank p, but they are linearly dependent if that rank is less than p. Theorem 3, the rank R of a matrix A equals the maximum number of linearly independent Coulomb vectors of A. So your A and its transpose AT have the same rank. So your B transpose A transpose is equal to rank of AB. Similarly, rank of A is equal to rank of B does not imply that rank A square is equal to rank B square. And your rank of a product of matrix cannot exceed the rank of either factor. Okay? So tomorrow is there my class? Or today is my last class? Anybody?
Sir, I have a doubt.
हाँ बताइए एक या दो चार डाउट पूछो.
Sir, block 1 row of example number 1.3.
ओ जब स्क्रीन में दिखेगा ना मुझे क्या, मैं तो भगवान नहीं हूं ना, आप 1.3 1.9 बोलेंगे तुरंत पता चल जाएगा. So
Is the
we
screen
shall
check
discuss it
करते
if you show it in the screen.
Okay, sir.
Show it. Now my question is today is my last class or tomorrow is my class?
Tomorrow also.
Okay. So the rest we shall discuss tomorrow. क्या है 1.3 दिखाइए.
हाँ सर दिखाती.
हाँ आ गया. इक्वेशन दिखाइए. नहीं आ रहा है. यू रीड इट आउट. आप पढ़ लीजिए उसको. यू कैन रीड इट
कहाँ
आउट.
पर कैमरा है पता नहीं.
दिख नहीं रहा है. एनीबॉडी who is capable of reading the screen? No. So you can read it out.
Sir, consider a solid sphere of radius r.
हाँ.
सर क्वेश्चन बोल रही हूँ.
Question is wrong.
कैमरा कहाँ पर है पता नहीं.
So you get prepared and tomorrow we shall discuss that. Okay.
Yes, sir. One have
Thank you. The next class is Professor G. Nath. Please wait. Thank you.
Thank you, sir.